Hola, I'm Dora, the electrical engineer.
Hola, I'm Diego, a self-taught mathematician.
Hola, I'm Boots the monkey.
We've been climbing for 5 days to reach the top of Mount Lagrange.
This must be where the participation points are. Oh look, there's a door.
That must be our first challenge.
There are 3 doors, 3 puzzles. You must solve them all to get to the treasure. Oh, and I forgot to mention, there's a time limit, and there's a catch. The timer is on the RC circuit, and when the capacitor is fully charged, you will be trapped doing epsilon delta proofs forever.
What's a capacitor?
Now, it's easy to get lost in the math behind deriving these functions, so we'd like to remind you about how prevalent capacitors are in our lives. Using calculus, we're able to model functions that tell us about their varying charging and discharging behavior over time and take advantage of it for one of their many applications, including televisions, smartphones, computers, camera flashes, microphones, and power supplies. They help by removing electronic noise and signals that comes with traveling through wires and nearby magnetic and electric fields. They make video and audio more clear and eliminate distortion, which lets us watch YouTube and TV, make phone calls, and even record videos.
A circuit is just a series of electrical components connected by wires to allow current, which you can imagine is being pumped by a battery, to flow through it.
When current passes through these components, they have what's called a voltage drop. You can imagine it like a river where a battery is a pump pushing water up a hill, and whenever there's a component like a resistor or capacitor, there's a drop in height. The big idea is that the sum of all the voltages should add up to 0, where batteries are considered positive and the other components have drops, or negative.
Now resistors have a voltage proportional to the current passing through the resistor, V equals IR. However, capacitors are a bit special. A common ideal capacitor is a parallel plate capacitor, which is simply 2 conducting sheets, often metal, with a gap in between them. When current flows to the capacitor, it begins accumulating charge on the plates and thus inducing a voltage where it begins acting like a resistor, whose voltage depends on the rate of change of charge, which in turn changes the voltage on the capacitor.
As I said before, the sum of voltages must equal 0 in this case, so we can set up a first-order differential equation to find charge as a function of time, and with it, how long it will take the capacitor to charge up.
As we mentioned earlier, the sum of all the voltage drops must equate to 0, and power sources such as batteries are voltage gains, while other components are voltage drops, where they're negative. We plug in the formula for voltage drops across a resistor, V equals IR, and the voltage drops across a capacitor, which is V equals Q over C, where Q and I are varying with time. Here, we set up our equation and plug in I equals dq dt and solve for dq dt. Then we separate variables and use U substitution to integrate both sides. Now we have a general solution, which represents all the possible solutions of the differential equation we started out with. It can also be interpreted as the family of curves that satisfy the slope field represented by the differential equation. Since the capacitor is starting out discharged, Q at time 0 must be 0. So we can solve for our constant of integration K and get epsilon C. Now we have charge as a function of time. And since we know current is a derivative of charge with respect to time, then the function for current is just the derivative of the equation we just derived. Plugging in I and Q into our equations for voltage drops across the resistor and capacitors yields the following equations. Here we sketch the graph of charge stored in the capacitor, and we can see that it asymptotically approaches a value, epsilon C. So in about 5 time constants, where a time constant is defined as the product of R and C, the capacitor is fully charged. And in this case, our resistance is 2 ohms, whereas our capacitance is 5 farads. So the time constant must be 10 seconds. So in other words, we have about a minute, which is 5 time constants, to solve this problem. That's not a lot of time.
We don't have that much time left.
Oh no, let me think. 1 plus 2 is 3. Onwards.
Oh, there's a second door.
Now, you must solve the problem in the time it takes for the lights powered by the capacitor to go out.
Okay, let's figure it out.
Now, discharging capacitor is not very difficult to grasp after going through the work for a charging capacitor. The circuit now looks like this, and the capacitor now acts like a battery in a way to power the light. Capacitors are used in this way very commonly to discharge. Now we set up our equation just like last time, but now the voltage across the capacitor is positive since it is acting like a battery. This simplifies things greatly and we can easily solve for dq over dt, separate variables, and solve our differential equation for a general solution. Since the capacitor is starting off fully charged, we know that q at time 0 must be epsilon c, so we can solve our constant of integration out to be epsilon c. Now we have the particular solution modeling the charge in the capacitor as a function of time. Again, since I equals dq over dt, we just take the derivative to find current as a function of time. In approximately 5 time constants, the capacitor will be discharged, which yields approximately a minute, just like when we are charging a capacitor. I hope you can solve the puzzle in that time. An obvious example of an application of capacitors in circuits is exactly what we just did. RC circuits are often used to create a sophisticated and reliable timer using LEDs or speakers. Another very cool example is at the Lawrence Laboratory, where they power a high-intensity laser using a large array of charged capacitors that discharge at approximately 400 megajoules. According to their website, that's more power than the entire United States uses in that same fraction of a second.
What's 7 times 9?
This is super easy for a self-taught mathematician like myself. 63.
Look, it's the last door.
Finally, a time challenge. This time, you must solve the problem in the period of an oscillation of an LC circuit. Good luck. You'll need it.
What's an LC circuit? Now we're going to introduce the inductor. Whereas capacitors store energy in the electric field created by the charges it stores, inductors store energy in the magnetic field produced by a varying current through it. Both capacitance and inductance are properties of the specific capacitor or inductor depending on dimensions and materials. An LC circuit is comprised of an inductor and capacitor in series. The energy stored in the capacitor U sub C equals 1 over 2C Q squared, where C is the capacitance and Q is the charge in the capacitor. Energy stored in an inductor U sub L equals half Li squared, where L is inductance and I is current. The sum of energy must remain constant by conservation of energy, so the derivative of the sum of the energy in the capacitor and inductor must equal 0. We apply chain rule to both terms, cancel out I and dq over dt since they're the same, and plug in I equals dq over dt before solving for d squared q over dt squared. Now this is a second order differential equation since we're dealing with second derivatives. Ask yourself, what function second derivative is proportional to itself? The cosine. Now we skip much of the technicalities with the constants, but it comes down to a cosine function that matches the oscillatory behavior we described earlier. One period of this oscillation of the LC circuit is defined as 2 pi over omega, where omega equals 1 over root LC. Thus, if our inductance is 2 henries and capacitance is 5 farads, our period is 2 root 10 pi seconds. Will we be able to solve the puzzle in that time?
Again, current is the derivative of charge as a function of time, and from that we can see that current is also a periodic function with sine. We can conclude that the current oscillates back and forth between the inductor and capacitor. If the capacitor starts off with all the energy in the system, then it discharges into the inductor where it stores it in the magnetic field, which then induces a current that goes back into charging up the capacitor, and it oscillates back and forth.
Inductors paired with capacitors are used very often in household electronics, including televisions and radios for tuning frequencies, calibrating clocks, and transformers, which are used to power our homes.
Integral secant x dx.
That must be ln of the absolute value of secant x plus tan x. Yay! Look, that must be the participation points!
Oh no, we're too late. It's Swiper.
Everybody repeat after me. Swiper, no swiping!
Swiper, no swiping. Swiper, no swiping.
Aw, man!
Yay, good job, guys! We got the participation points!
We did it!
Yay!